Okay, in today's class, we did a lot of discussion and mostly posing problems and letting the class discuss them while I stayed around, but not close enough to participate in the discussion. Then I participated in some of the discussion after a while. Okay. The problem that we're trying to get our hands on is if you've got a kilogram of the metal of your choice, okay? How do you configure it in order to get the maximum possible magnetic field? Now, we've observed the Helmholtz coil, okay? Would you do something like this? Well, just make sure we have our heads around this. We talked about what was done in lab, and this has already been posed, but nobody had really worked it through, I don't think. We observed in this configuration that when we ran a 0.6, roughly a 0.6 amp current through it, which was some combination of a few 1.5 volt batteries um, in series. We observed a magnetic field in this area in between around 2.5 milliamps. Okay, now that's tens of times stronger than the Earth's magnetic field. It's a pretty significant magnetic field. And of course, that's used. You can put a vacuum tube in here with various configurations, and you can measure the deflection of an electron in a magnetic field and stuff like that. Okay, all kinds of things you can do. We're not going to do most of those experiments, but we can do them. They can be done. I'm not sure the tubes even work anymore, but here it is. So we figured it out. Okay. Then we figured out that, well, you got 0.6 of an amp. Let's just call that an amp of current. And let's just take one loop and field at the very center of that loop and talk about what that field would be. Well, if we got 1 amp in a loop of radius 10 centimeters, then applying the Biot-Savart law to every little increment along that loop, we find that that increment is in a direction that's perpendicular to a vector from that increment to the center of the loop. That would be your R vector, vector from the current element to the center of the loop. So when we calculate that, long story short, we just add up. Every increment is going to give us the same thing if we use equal increments. In every case, the current is going to go, we're going to end up with a magnetic field perpendicular to the plane of the loop. If the current's going this way, it'll be like so. Everybody is on top of that. Okay, everybody understands most of that. The whole thing about being able to use the whole length of the loop as the length in the Biot-Savart law. Not sure everybody completely understands that, and people really need to. In any case, we end up with a total length there of about 0.6 of a meter. So let's just call it a meter. Let's just say we got a current of 1 amp in a meter of wire of radius 1/10 of a meter. Now that's not right, it's 0.6 of a meter, but we've got to use a 1/10 of a meter to calculate the fall off of the magnetic field and all that stuff. We end up with an IDL total of 1 amp meter. And we multiply that by K prime, 10 to the negative 7th Tesla meters per amp, and divide by the square of the distance down here. And we get something on the order of 10 to the negative 6th Tesla. Came out something times 10 to the negative 6 Tesla, and wouldn't for the numbers that I have here. I think it comes out around 4 times 10 to the negative 6 Tesla. When you then take 60% of that amp and 60% of that circumference. Then when you multiply that by the number of loops, it's somewhere between 100 and 200 loops in the whole thing. The point in the center here is not really at the center of any loop, but that doesn't make a huge amount of difference. It's kind of a cosine error, and I'm not going to talk too much about that because I want people to think about it. Okay? So is it plausible that that should give us about 2.5 millitesla? Might have said milliamps, millitesla field at the center. And then use this idea, once you have a good grasp on it, to think about how you would configure that kilogram of metal. Would you make individual loops? I asked, well, what if it wasn't 170 loops? What if it's just a continuous chunk of copper, same dimension, just one ring of copper here and another ring over here? Okay, well, another ring over here. Okay. Would you have the same field, or would there be some difference? I even pointed out at some point that if you had the equivalent amount of copper in a loop, the copper equivalent of all those loops in one circular ring, you would have 1/70th of the resistance. Okay. You'd also have 1/70th of the number of loops. Is that a wash? Or are there things I'm not telling you? Are there things that are otherwise relevant? But if you have 1/70th the resistance and 1/70th the number of loops, does that not give you the same current? Okay, that you would have in all those loops of wire. Okay. In which case, just having these things in one continuous ring would be equivalent to what you have in the 70 or so loops that are present. Then we ask, we also look at the solenoid, and walk over here just a little bit to find it. Looked at the solenoid, discussed Ampere's law, used this domino to represent a rectangle. And now if we take this rectangle down here and insert it, now if it's an imaginary rectangle, if we insert it so that the lower edge runs inside the loop and the upper edge over the top, what would the total of the B dot ds be? Okay. The length of this thing is 5 centimeters. Okay. If the magnetic field is constant in this section, or very nearly constant, then what is the B ds? Letting B remain as unknown for the time being. Well, ds, it's 5 centimeters. Okay. You know how much current is enclosed. Okay, well, I say, let's just run an amp through this wire. It's about a 10 ohm resistance. We probably need about 10 volts to get an amp. Might get a little warm, so we don't want to run it for too long. It's going to create a magnetic field inside here. Every loop is going to give you a magnetic field in that direction if the current's going around like so, okay? You can easily solve for the magnetic field if you know the current enclosed. By the current enclosed, that means the amount of current that passes through the rectangle here. Now, this is an integral over a curve. Well, here's a statement. I enclosed is the total current passing through a surface bounded by the curve C. Now, there are more restrictions on what kind of a surface you have. You don't want it self-intersecting, and you don't want it to have a lot of holes in it or stuff like that. But by some continuous surface, some reasonable surface bounded by the curve C. The simplest would be simply the face of this rectangle, okay? And the boundary would simply be the boundary of the rectangle, the rectangle around the interior, okay? Through the interior of this, if we drop this through here, we might have 50 turns of the wire. So if we have a 1 amp current, we have 1 amp in each loop of wire. And if we cut 50 of them with this surface, we're going to have 50 amps. That'll be your current enclosed. So if you use 50 amps here and 5 centimeters for your delta S, assuming B is constant, you can easily solve for B. And you really need to understand that and be able to do that. The other thing I mentioned is that's assuming that all your BDS is along the lower edge of this rectangle, which is inside the loop. The upper edge is outside the loop. There's also BDS. There's also a magnetic field there. But if you let this domino keep the lower edge in there and just expand this domino to make it a mile high, then there's essentially no B along the top. Also, there's no contribution to B.ds here. If the magnetic field is this way or this way, it's perpendicular to your ds along any increment of the path on the end or the path on this end. Okay, so that the orientation of your curve here and here is perpendicular to magnetic field, contributes nothing. So the only thing that really contributes, if you make this thing a mile high, is magnetic field inside the loop along this 5 centimeters. Okay. So apply Ampere's law. Look it up. Read your book. There's pictures of this in your book. Okay. Use AI. Don't use AI to get the answer and forget it. Use AI to understand. Okay, if you use AI just to get the answer so you can go on and get another answer and get some credit, you're going to be dumbing yourself down compared to what you would be doing if you used AI to help you understand. And just getting the right answer does not imply that you understand. I think people know that, just keep it in mind. So use whatever source you want to understand this and how it applies to this and other things and how it applies to our ultimate question, which goes back to this kilogram of metal that you could make into a cylinder. Okay. It might be a kilogram of gold. That'll be more than a kilogram to make this cylinder. Would that be a good configuration, or would it be better to have a thinner disc, bigger diameter here, and kind of a hole in the middle? You want to get the current as close as possible to the point where you're going to have the maximum magnetic field, which is our goal here. Find the configuration that gives you the maximum magnetic field. Is a cylinder or a solenoid going to do it? Is a set of Helmholtz coils going to do it? Is a big ring with current flowing around the ring going to do it? Okay, well, speaking of currents flowing through different configurations, let's go to a slightly different problem. Got a source and we've got a bunch of wires. So assume the wires have negligible resistance. And assume this triangle, and let's just consider this to be a flat triangle cut out of some material with lowish conductivity, so there's significant resistance here. Okay, so that essentially all the resistance in this circuit is in this thing. Okay, conductivity low enough that that's the case, resistivity high enough that that's the case. Then I want to know how the electrons are moving in here. And we discussed it. People said, well, doesn't it split into two? The electrons moving along here and electrons moving along here. Well, this is not a wire. It's actually solid. And the way I drew it, I could understand that, but let's just go ahead and make sure we understand that this thing is a solid piece, a flat, solid triangle with some thickness, made of some material with lowish conductivity. It's not an insulator, but it's not a great conductor either. And if you want, you make it a solid or revolutions. This is a cone. That'd be fine. Conceptually, they're not that much harder to deal with. My question is, how does current flow? It doesn't just flow along the edges. Okay, the charge, the free charge, has to remain almost perfectly uniform in its distribution through the volume. Okay, uniformly distributed conduction electrons throughout the volume. This is metal. Let's assume this is something that engages in electron conduction. Okay, not necessarily a metal, but something that okay. The charge carriers will assume to be electrons in this case. All right. So the question is, how do the electrons move through this? And what can you tell me about the motion of the electrons? Okay, what can you tell me about anything about the current and so forth? Well, after quite a bit of discussion, people came to the fact that the current has to be constant. Current passing one point has to be the same as the current passing another point for the simple reason that current can't accumulate, charge can't accumulate. If it does, things blow up. People get killed. Depends on just how bad the accumulation is. So you can't have it unless you got some capacitors or some equivalent in the circuit. You can't have an accumulation of charge. Charge keeps moving. So the charge that moves past this point is the same. The rate at which charge moves past this point is the same as the rate at which charge moves past this point. Is the same as the rate at which charge moves through your source. It's the same rate at which the charge passes through any point. Now, when I say any point, I mean, like here, 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 here. Okay? And then people kept thinking that we're getting too far, and somebody said, well, it's kind of like a water fluid. If you have a flow through this thing, the water's going to have to be flowing faster at the narrow edge than at the wide edge. Well, that's really a good analogy. Okay? You have the same electron density throughout this thing. The only way the current down here in the narrow part is going to equal the current in the wide part is if the electrons are moving faster. And it's a simple proportionality. Okay? Now, once you have that insight, I raise the question is, what is it that results in the electron cloud moving faster at some points than others? I even got a little more specific. I want a vector. People want to explain it by saying, well, because it gets narrow, so they have to move faster. That's not what makes them move faster. They have to move faster, but something's got to make them move faster. What is it? What is it in the conduction model? And nobody came up with it. Nobody came up with either of two vectors that are relevant to this. Okay? At which point I said, you really need to know what vectors are involved. Somebody said, I don't think the vector that's involved there came up in the introductory problem set. Could be. Could be. I don't think I necessarily talked about it, but I'm not sure because I've built those things over 30 years ago, or about 30 years ago. But of course, you got your text and you're responsible for, at least scanning through your text, looking at the chapter reviews and so forth, so you can answer some of these questions. You can even use AI. You can go online. Okay. Well, I finally went to the extent of said, okay, look, I'm going to do it. I'm going to go up to the computer here and I'm just going to put in electrical conduction model. Well, it gave me a pretty sophisticated model, something beyond the scope of this course. Talking about collisions of electrons with ions and so forth. And nice model, not that difficult to understand. If you understand the conduction model as we're doing it in this course, you would be ready to understand that model. Okay, but we're not there. We don't want to make that big jump. So I then appended, and I just put this in the address box of my browser, Chrome browser. I just appended, okay, at the level of a calculus-based physics course. Okay, gave me kind of the same stuff, but with a little simpler explanation, about that much of it. And then right below that, it gave me the answer to this question. Okay, which when you see it, you should do the usual, draw a little circle on the blackboard and stick your head in it. Okay, bounce your head against it. Because it's one of those things that you're going to recognize. We've talked about it a number of times. We developed it in the conduction model some time ago. You ought to know it. Not surprising that you don't. Got a lot of things to do, and procrastination is universal. So I understand that, but I'm still going to test you on it. Okay. So you probably ought to review. You probably ought to take better notes and review them once in a while. I also quoted a study. Now, the study hasn't been replicated or anything. It looked like it's been done pretty well, but it's a neurological study, and I don't know that much about that field, but done by a pretty reputable group, and it's getting a lot of attention. I think that if you study the same thing every day at the same time, 24-hour intervals, that's optimal for learning. And I suggested you set aside 5 minutes, 10 minutes, whatever you can afford, and hopefully with a little bit of time on the end in case you get inspired, and think about these things and work on these things until you understand them. Okay? Every day. Try to enhance your understanding a little bit. Think about the problems I'm posing. Think about this problem. Think about what's going on here, why you should know the answer to this question, but mainly know that you make sure that you always know the answer to this question in the future. Okay? You can visualize it. It's not difficult to understand, but it's fairly sophisticated. I won't say that I understood it 100%. I mean, I could do it when I took the course, hundreds of years ago. But among physics majors, sometimes I scored pretty high. Sometimes I didn't score as well. Okay, and I ended up changing my major to mathematics. So I wasn't the rocket scientist of the group, but I did okay. And I still found this a little bit challenging when I first saw it. So if you're finding it challenging, that's about what you expect. If you're not finding it challenging, that's a very good indication. It means you're doing real well. Okay. Again, 24-hour intervals. Experiment with it. Try it. See if it doesn't have benefits, because if it does, you might get in the habit of using that to the extent that it's possible with all the other demands in your life, to reduce the amount of time and increase the efficiency of your learning. Okay? Decrease the amount of time you spent for a given level of learning or even for a higher level of learning. Okay, well, good luck with that. Don't take that as being an ironclad method, but there's enough evidence right now to merit a 5-minute-a-day experiment for a couple of weeks. And I would encourage you to do that. Okay. Well, there are going to be more problems, but see if you can really understand these problems completely.